Hi everyone. Today we're going to continue our discussion of atomic weights, and today we're going to apply that to the calculation of molecular weight. So the relative mass of a molecule in atomic mass units is called the molecular weight of the molecule. And because molecules are made up of atoms, the molecular weight of a molecule is obtained by adding together the atomic weights of all of the atoms in the molecule. So, for example, we have water, which is H2O, and down below we have the periodic table depictions of hydrogen and oxygen. So last time we said that the values at the bottom of these squares here are the atomic weights of each element. And remember that those atomic weights are actually averages of a collection of atoms or isotopes. Okay, so if we want to find the molecular weight of water, we have 2 hydrogens and 1 oxygen. So we're going to add all of those together. So we're going to multiply the atomic weight in atomic mass units of hydrogen by 2. And then we're going to add the atomic weight of oxygen. So the value that we should get is 18.016 atomic mass units. And here's another way of looking at the calculation. So here, to start, we have the atomic weight of hydrogen multiplied by 2 plus the atomic weight of oxygen multiplied by 1. Now, you'll notice that here we have a rounded version of the atomic weight of hydrogen. Sometimes that just depends on the periodic table that you're looking at. Some periodic tables will carry out the atomic weight to 4 significant figures. Some only use 3. It just depends on which one you're referencing. But you should still get a very similar answer. So you'll notice here we still have an answer of 18.02 atomic mass units. So let's practice calculating molecular weight, and this time we're going to calculate the molecular weight of carbon disulfide. So you might remember from a previous video that this clear liquid at the top of this figure is carbon disulfide, and we determined that the molecular formula is CS2. So that means that we have 1 carbon and 2 sulfur atoms. Now, if we look at a periodic table, and this is just an example of one periodic table, there are many out there. Carbon is in the upper right-hand side of the periodic table, and its mass is 12.01 atomic mass units. And then sulfur is near carbon, and it has an atomic mass or weight of 32.06 atomic mass units. So let's go back and we'll write those down. So to calculate the molecular weight, or sometimes we'll call it the molecular mass, we're going to add together the mass or weight of one carbon atom and then the mass of two sulfur atoms. And that should give us 76.13 atomic mass units. So that is the molecular weight for carbon disulfide, or CS2. Now, this is all leading to a concept called the mole concept. So the mole concept is going to allow us to count, for instance, the number of atoms we have or the number of molecules that we have. So when we talk about moles, we're not talking about the animal. This is, again, just a way to count. So the number of atoms in 1 mole of any element is called Avogadro's number. And that is equal to 6.022 times 10 to the 23rd. So this is a really large number. But this number is similar to a baker's dozen. So if we say that we have a dozen of something, that means that we have 12 of that something. So if we have a dozen eggs, that means we have 12 eggs. And it's the same exact thing with the mole. If we say we have 1 mole of anything, then that means we have 6.022 times 10 to the 23rd of that item. So Avogadro's number, again, is 6.022 times 10 to the 23rd. And this is going to be a really key equality that we're going to use a lot. Now, you'll notice that the unit listed next to Avogadro's number is items, but this could be anything. This could be atoms, molecules. Maybe we're counting how many cats we have, or pencils. So your unit there could be whatever you're counting. Now, obviously, this is a very large number, so we're not going to use this to count cats or pencils. We're going to use this to count really small items like atoms and molecules. Now, a couple more things about this mole concept. A 1 mole sample of any element will contain the same number of atoms as a 1 mole sample of any other element. And then additionally, 1 mole of any element is a sample of the element with a mass in grams that is numerically equal to the atomic weight. So down below, our first example is sodium. And remember that the symbol for sodium is Na, because its original name is natrium. So if we have 1 mole of sodium, that means that we have 6.022 times 10 to the 23rd sodium atoms. And then down below, if we have 1 mole of calcium, that means that we have 6.022 times 10 to the 23rd calcium atoms. So that is showing us what we said earlier, that a 1 mole sample of any element will contain the same number of atoms as a 1 mole sample of any other element. Now, in terms of the second point we went over, if we look up the atomic weight of sodium, we would find that it's equal to 22.99 atomic mass units. But we can also set this equal to 22.99 grams of sodium for every 1 mole of sodium. So this unit is called grams per mole, or the molar mass. So what this really tells us is that 1 atomic mass unit is equal to 1 gram per mole of that same element. So down below, if we have 1 mole of sodium, that also means we have 22.99 grams of sodium. Or 1 mole of sodium weighs 22.99 grams. So if we took a balance and we added 22.99 grams exactly of sodium, we would end up with 1 mole of sodium, and we would also know that we have 6.022 times 10 to the 23rd sodium atoms. So mass and moles are tightly related to each other, but additionally, this is also tied in with counting and keeping track of how many atoms we actually have. Now, additionally, calcium, if we look up calcium's atomic weight on the periodic table, it is 40.08 U, but that's also equal to the same amount in grams per mole. So if we have 1 mole of calcium, that means that we have 40.08 grams of calcium. Now we can also apply this concept to compounds. So again, a 1 mole sample of any compound will contain the same number of molecules as a 1 mole sample of any other compound. So down below we have 3 examples, and we can see that if we have 1 mole of water, that means that we have Avogadro's number of water molecules. If we have 1 mole of CO2, which is carbon dioxide, we also have Avogadro's number of CO2 molecules. And if we have 1 mole of NH3, which is a molecule called ammonia, that means we also have Avogadro's number of NH3 molecules. And then 1 mole of any compound is a sample of the compound with a mass in grams equal to the molecular weight of the compound. So earlier we determined that the atomic weight, or molecular weight, of water was equal to 18.02 U, and we can also say that that is equal to 18.02 grams per mole. So if we have 1 mole of water, that's going to weigh 18.02 grams. Now, we can also do the same thing for CO2 and NH3. If we calculate the molecular weight of CO2, it comes out to be 44.01. So if we have 1 mole of CO2, we also have 44.01 grams of CO2, and we have Avogadro's number of CO2 molecules. And then the last example, if we calculate the molecular weight of NH3, we would find that it weighs 17.03 atomic mass units. But additionally, that means that if we have 1 mole of NH3, then that will weigh 17.03 grams. Now, the mole concept can be used to obtain factors that are useful in chemical calculations, And we can use these factors for both elements and compounds. So down below we have a few different examples of elements and compounds, and everything is in a 1 mole amount. So over here we have 1 mole of copper, and if we look on the periodic table, the mass of copper, or the atomic weight of copper, is 63.5 grams. And then in the middle here, we have a ball of aluminum foil, and we actually have 1 mole of aluminum there. So that will weigh 27 grams. And if we look on the periodic table, the mass of 1 mole of aluminum is 27 grams. All right, and then over here we have a sample of lead, and we actually have 1 mole of lead. And that's 1 mole of lead is equal to 207.2 grams, which is the same as the atomic weight listed on the periodic table. And we can keep going. So down below we have a 1 mole sample of sulfur, a 1 mole sample of chromium, and then a 1 mole sample of magnesium. So all of these different samples contain Avogadro's number of atoms. But each atom is going to have a different mass based on what we see on the periodic table. So sulfur, for instance, weighs 32.1 grams per mole, whereas lead weighs 207.2 grams per mole. So even though it looks like we have different amounts of each element, we actually have the same number of atoms, it's just that they're going to weigh different amounts. And then on the right-hand side, we have 1 mole quantities of 4 different compounds. So in this graduated cylinder on the left here, we've got 1 mole of H2O, water. And again, that weighs 18 grams approximately. And then in this small beaker, we have 1 mole of sodium chloride, which is table salt. So that's the salt that you put on your food. And that weighs 58.4 grams. And then in these larger beakers, we have 1 mole of aspirin. But you'll notice that aspirin contains a lot of atoms itself in 1 molecule. So aspirin, or 1 mole of aspirin, will weigh 180.2 grams. So that's why it looks like we have a ton of aspirin there. And then this green compound is something called nickel 2 chloride, hexahydrates. And that's also a 1 mole sample. So all of these samples contain Avogadro's number of molecules. However, they're all going to weigh different amounts based on how many carbons or hydrogens or oxygens there are in the compound. So let's actually go over some mole calculations because this will become important later on in chemistry. And the mole-based relationships given earlier are examples, or as examples for elements, provide factors for solving problems. So we can turn all of those equalities that we saw earlier into conversion factors. So for instance, we said that 1 mole of calcium is equal to 6.022 times 10 to the 23rd calcium atoms, and then that's equal to 40.08 grams of calcium. So we could create up to 6 different conversion factors here. So down below are examples of 2 of those possible factors. So maybe we write that we have 1 mole of calcium over 40.08 grams of calcium. We could actually flip that as well, depending on what we're trying to solve for. So if we are solving for moles of calcium and we're trying to get rid of grams of calcium, then that conversion factor is fine the way it is. But maybe we want to solve for grams of calcium and we want to get rid of moles of calcium. Then we would flip that conversion factor. And then in the second example, we have 40.08 grams of calcium over Avogadro's number of calcium atoms. So if we're solving for grams of calcium and we're trying to eliminate atoms of calcium, we can use that, or we can flip it if we're trying to solve for atoms of calcium and we're trying to cancel out grams of calcium. So there are a lot of possibilities here in terms of conversion factors and what we can use to solve problems. So let's calculate the number of moles of calcium contained in a 15.84 gram sample of calcium. So to start, let's write what we're given. So we're told that we have 15.84 grams of calcium. So maybe we weighed this on a balance. And now we want to determine how many moles of calcium we have. So our plan of attack is going to be, okay, we need to go from grams to moles. And remember earlier we saw that the molar mass of calcium is in units of grams per mole. So 1 mole of calcium is equal to 40.08 grams of calcium. So again, this is called a molar mass. Oh, didn't mean to do that. And we're going to use this molar mass as a conversion factor. So let's set up our problem. And again, we're always going to start with what we're given. And then I like to set up a little line for my conversion factor so that I have the numerator and the denominator handy. So now we have to determine which unit we want and which unit we don't want. So we already said that we want moles of calcium. So we're going to put this part of the equality, 1 mole of calcium, in the numerator. And then we're going to put 40.08 grams of calcium in the denominator. Okay. Now, the reason we did that is we're going to cancel grams of calcium and end up with moles of calcium. So now we have 15.84 divided by 40.08, and then our final unit is moles of calcium. So if you want to plug this into your calculator, feel free to pause the video and see what answer you get. And then when you restart the video, we'll go over the answer. The answer I got was 0.3952 moles of calcium. Okay, so not too bad. This is very similar to problems that we did in Chapter 1, but this time we are using the mole concept. and atomic weight. Now let's do one more problem. Let's calculate the number of atoms in 0.5 moles of calcium. So let's start by writing out what we're given. So we're told that we have 0.5 moles of calcium. And we need to determine the number of atoms of calcium. So our plan of attack is to convert moles to atoms. And earlier we saw that Avogadro's number tells us 1 mole is equal to 6.022 times 10 to the 23rd of whatever we're counting. And in this case, we're counting atoms. So let's set up our problem. Again, we start with what we know or what we're given. And I'm going to write out my little conversion line there. And in the numerator, we want to put the desired unit, which is atoms. So we're going to write 6.022 times 10 to the 23rd atoms. And then in the denominator, we want to put the unit we're trying to get rid of, which is moles. So we're going to put 1 mole of calcium in the denominator. Okay, so now we're canceling units of moles, and we're going to end up with, go back to red, 0.5 times 6.022 times 10 to the 23rd. And then our unit is atoms of calcium. So if you would like to pause the video and plug this into your calculator, feel free. And the answer we should end up with is 3.011 times 10 to the 23rd atoms of calcium. So that's half of Avogadro's number. All right. So we're going to end the video here. I did post a worksheet on Canvas, and that worksheet steps through some example calculations for calculating molar mass as well as determining the number of atoms in a sample, or the number of moles that you have, or the amount of grams, so the mass. And I will see you in the next video.